We have made it to the end of chapter 5, the last section in the chapter, 5.7. And this is going to basically go in reverse from the previous lesson, the 5.6 lesson, which was deriving inverse trig. We're going to look at integrals that are inverse trig model integrals. It is the last integration form for Calc 1. Unlike derivatives that are actually done and there's no more derivatives in any calculus, integration, there are actually more forms and more techniques, but they're all Calc 2 techniques. So this kind of ends the Calc 1 discussion of how we integrate. So when we're looking at these, if you think back to the 6 derivative rules from 5.6, for integration, we narrow it down and we only look at the positive ones. So arcsine, arctangent, and arcsecant. Those are the only 3 forms we're going to look at. Now, they're kind of interesting. So your denominator is going to determine which one it is. Whether it's arcsine, you're going to have a square root. A is going to be a number. It's a constant value. In your arcsine, the constant value is always going to come first. So you have the square root of this a squared minus u squared. For your tangent, now tangent was the one that was the most unique with derivatives, and you'll see the same with this. Tangent has an addition, and it has no square root. It is a squared plus u squared, or you could write it in reverse, u squared plus a squared, because it's addition. And then secant has the most bizarre look. It's also the least common. Again, arcsine and arctangent, pretty common. You'll see that maybe once or twice. Probably won't see secant, but I'm still going to put it up here so you have a full list. With your secant, it has the u piece out front of the square root, and then it has the square root of u squared minus a squared. So when you work with these, you're actually going to make a list of 3 things with these. You're going to write down your constant value, which is your a, so what number was squared, your u value, which is a function, what function was squared, and then your du, and for this, you are going to check and see if there's a du adjustment that needs to be made. A lot of these problems, when you first see them, they'll look like regular u sub, they'll look like power rules or natural log, but because of what's in the numerator or what's not in the numerator, they end up being inverse trig. And I'll take you through what that means as we go. I would say have this list written down somewhere. Pause the video if you need to make sure they're written down, and then we'll use it as a reference for the entire class. We're going to go through examples. I will show you some special types as we go. First thing you want to notice is which inverse trig function it is. Maybe even before that, I do want you to realize why this is not just a regular u sub. So I'll start actually with that conversation. In a normal situation, when you see a problem like this, your first thought will probably be to let u be whatever's under the radical, because that's the piece that's having something done to it. Well, the derivative of that, of the 4 minus x squared, is negative 2x. Notice your numerator does not have an x in it. Because of that lack of an x, a lack of the du, I can't do a regular u sub and treat it as a power rule. That's usually what I would try first. I would actually, inverse trig wouldn't be the first thing that comes to my mind. I would go back to maybe something a little more basic. But once that doesn't work, because we don't have this x value, now we want to think, okay, inverse trig, I've got 3 options. Does it fit one of those 3 models? This is going to be an arcsine. 2 things you'll notice. It has a square root, which means it can't be tangent, and the number comes first. So I'm going to write down my list of 3 things, a, u, and du. Your a is going to be 2 because that's the number that was squared. Your u is going to be x because that's the variable that was squared. And the derivative of x is just dx, or 1, which means there's no adjustment that's needed. Once you have all your 3 pieces, you're just going to put it in the form from what you saw before. So let me go back to these forms for a second. The arcsine is just arcsine of the u value over the x value. Arctangent and arcsecant have an additional coefficient. This is a little different here and here. It has a 1 over a. The sign doesn't have that, but it's still arctangent of u over a or arcsecant of u over a. So with this one, it is just the arcsine of x over 2. You can put that in parentheses if you want, or you can leave it as is. Second one, same thing. If you look at this and think of it as a u sub and let the bottom be u, the derivative of the denominator has an x in it, and there's no x on top. So I can't treat this as a u sub, but it does work out to be a really nice inverse tangent. No square root, it's got an addition. Your a is 4 because that's what was squared to get 16. Your u is 3x because that's what was squared to get 9x squared. And your du is 3, which I don't have in my original integral, so I am going to have a 1/3 adjustment. As far as what's being done to it, what form it is in, this is an arctangent. Now, arctangent does have 1 over a out front, so in addition to the 1/3 adjustment, there's also a 1/4, and then the arctangent of u over a. And you can leave it like that, or if you want to multiply your coefficients, you could write it as a 1/12 of 3x over 4. You'll see a decent amount of arctangents. It actually might be the most common with this section. I think arcsine would be second place then. This one, my u, or let me start with my a. My a is 3. My u is 2x, and my du is 2. This one's kind of an interesting one. It's an arcsecant because it has the square root and it has the function come first. Now, normally with an arcsecant, I'm going to do this in a different color, the entire u should be down here. So in addition to an x in front of this square root, I should have a 2 as well because that's du. It is perfectly legal for me to put a 2 in the denominator there as long as I also put a 2 in the numerator. So this one's kind of different because by doing that, by putting that 2 in the bottom and putting that 2 in the top, I've actually made it perfect. I don't need to adjust anymore because I needed a 2 du on the top for du, and I have it. I have everything I need to make it a perfect secant. My arcsecant is 1 over a, so 1/3. Arcsecant, if you remember to put the u in absolute values, great. If you don't remember, I am not going to take off. Arcsecant isn't asked about enough to really get too technical with the little details like that. Next one is also an arcsecant. I think these are the only two arcsecant I'm going to do, and then I'm going to go back to the common ones. Your a is 1. Your u is e to the x because that's what was squared to get e to the 2x. And your du is also e to the x. So you've got your du on top, you've got your u in front of the radical. This is my u squared minus a squared. So I've got everything I need for my arc secant. 1 over a is just going to be 1 over 1. So I can skip that and just write arc secant of e to the x. Be e to the x over 1, but you just need to write e to the x. Let's go back to the signs, and actually I don't want to do this one. Let's do this next one. It's kind of a different looking form. So your a is not in the whole number because we have 5. So what was squared to get 5 was the square root of 5. It's perfectly fine for a to not be a perfect whole number. Your u is actually a binomial. It's actually x minus 3. The derivative is just dx, or 1, which is what you have. So you get 1 over the square root of 5, which you do not need to rationalize. This is an arctangent because it's addition of x minus 3 over the square root of 5 plus c. So let me show you what delta math is going to do, just so you get to see it. So on delta math, let me just pull one up. It is derivatives of inverse functions. Nope, not that one. I want integrals of inverse functions. Here we go. They are going to ask for you to write your answer in simplest form. So with this one, your u is going to be, let me mark this one up a little bit. Your a is going to be 3. This is an arctangent. Your u is going to be 2x. Your du is going to be 2. What I'm going to end up have happening is my 8's going to come out in front, but I'm also going to have a 1/2 out front when I adjust. So I have my 8 out front, I have a 1/2 out front, so I end up with a 4. This is an arctangent, so I also need 1 over a, so I need the 1/3 arctangent of u over a plus c. I haven't typed these into delta math much, so let's kind of see what this looks like. So this is going to be, get my screen a little bit better here. So this is going to be a 4/3 arctangent of 2x over, nope, I just want the 2x. Let me put that in parentheses. Probably make it easier to stand out. 2x. I really just want this to be over that. See if it lets me. There we go. 2x over 3 plus c. I want to take you through one just in case there were little things like that that were causing an issue. So it will run you through all of that, and your adjustment. Obviously, you can write it as 2/3 x. I wrote it as 2x over 3. Putting it in parentheses allows you to write it as a fraction. So there you have the basics. I got one last thing to show you in 5-7, but I'll make a separate video.